Rightio then. Rightio. We're on to our last little topic in vectors, which is looking at using vectors to solve geometrical problems. What I'm talking about is things like, is it a square? Is it a parallelogram, a rhombus, a straight line? And also this thing about a midpoint. That's all we're going to do. We're not really going to do anything amazingly new. We're just going to apply it to situations. So let's get cracking. So the first thing that we want to do is we want to talk about straight lines. Like, how can you use vectors to tell if something is on a straight line? So we're going to start with 3 points, A, B, and C. We're going to make it look like this. These are our 3 points, A, B, and C, and they look like they're on a straight line. We can maybe connect them up like that. But what if they weren't on a straight line? What if there was something like, here it's obvious they're not on a straight line, here they are on a straight line. What you would have if they were on a straight line is that the position vectors, the displacement vectors from A to B will be parallel with the one which is A to C or B to C. So let's get that in a little sentence. So this is what I've written. AB, the vector from A to B, is parallel to the one from A to C, which is parallel to the one which is B to C. This is not straight. This one is straight. If they're all on this straight line, we often use the word linear to say a straight line. So if they are on a straight line, then we say that they are collinear. A, B, and C are collinear. This is a double L for collinear. It's co as in like the complement, but then we've got linear, but it's a double L. So A, B, and C are collinear. If someone says 3 points are collinear, it means that we're all on a straight line. They all share the same linear line. So AB is parallel to this, which is parallel to this, but that's not the main point. Previously, we said that if two vectors are parallel, you can write one as a scalar multiple of the other. So here's the key point. This is the condition. Now we could swap this AC for BC, but it's still going to be true. It would be a different K. What you would find here as well is that this constant will actually describe the ratio of the length between these two. And that's it. Let's do an example, eh? I'll get an example written up. So here's our example, e.g. 1. We're probably going to have a few in this video. We've got this vector here. This is a displacement vector. Again, it goes from A to B, 3 minus 7. This one's C to A, which is minus 9, 21. It's going from C back to A to B, C back to A. Are they parallel? We're going to do this, find a solution for K. If we can find a K that makes it work, then they are parallel. Here, we're just going to do the simple kind of scalar multiplication. So we're going to multiply this K into each element of this vector. So it would be minus 9K. And on the bottom, 21K. Then you've got two simultaneous equations. This left-hand side, 3, the top element of this vector must be equal to the top element of this vector, since those two vectors are equal. So we've got 3 equals minus 9K, so K must be minus 3. And then we've got the bottom one, minus 7 equals 21K. Oh, that's meant to be 1 over 3. And this, same thing. If both of those two agree, and you get the same K, then means you've got a solution. If you've got like minus 1 over 3 and 4 there, then you've not got 1K which works for both, and which means it's not parallel. These are the same, which implies parallel. So this are collinear. That's our question. All right, I might just move this up, and then we're going to talk about midpoints. How do you find a midpoint? Yeah. Okay, we're talking about midpoints here now. So you may remember, like, if you want to find the midpoint between two coordinates, you're going to add them together and then half them. It's like taking the average of those 2 points. It's very similar for vectors. Now consider these two vectors here. Well, these are points. This is point A, this is point B. If we've got it in reference to an origin, let's say the origin is down here, origin, then this one, that's a position vector O to A. I'm going to call it A like that though, bold face A. That's just our position vector. Same going over here. B, But what we're looking for is the midpoint. That's M. And we want to know what is the vector that takes us from the origin to the midpoint. Okay, so if we want to get to that midpoint, we want to go up A, then halfway along this route from A to B. So let's just write that down. Okay. So that's half AB. What is AB though? Well, AB, remember I said this in a previous video that if you're going from A to B, then that's the position vector OB minus OA. So it's like A to B, you're going back down A, then up B. So it's going to be OB minus OA. But because we've labelled our position vectors A and B, this is just B minus A. We're going to stick this into there instead of that AB there. Then what we get is, which clearly simplifies down to just this next step, which I'm going to tell you. Half A plus half B, or more commonly written as that. And this is a little derivation of the vector, the position vector of the midpoint between 2 points, okay? This is something that in A-level maths you're expected to know, this derivation, and it's quite easy really, in my opinion. So let's do an example. Okay, here we go. We've got two vectors, A and B. A is 3 minus 5, B is minus 3, 1. We want to find the midpoint between those two, not just the midpoint, the position vector to that midpoint. So we're just going to follow this rule before. So, white chalk. OM is equal to a half A plus B. So it's a half A plus B. Let's just go straight in. 3 add minus 3 is 0. Minus 5 add 1 is minus 4. And then you just times that out by a half and you just get 0 times a half is 0. And minus 2 on the bottom. If you weren't sure, you could draw that as a little diagram. Like if you were 3 minus 5 minus 3, 1. Yeah, it seems reasonable, doesn't it? Whew, this is going well. So what we've got left in this final spot though is actually solving geometrical proper problems. Is it a rhombus or is it a parallelogram? Think about what is a rhombus and what is a parallelogram. What makes them different, okay? I'm starting to find a problem of wearing black and having a chalkboard. I'm just getting covered in chalk all the time. It's like, oh my God. Ah, jeez. This is a parallelogram, or is it a rhombus? It's definitely not a rectangle. It's like a rectangle which has been slanted over a bit. So what we find from that is that these two sides are parallel. That's what that means. And these two sides are also parallel, but they're not parallel with those two. The difference between a parallelogram and a rhombus is that the parallelogram is a rectangle slanted over, a rhombus is a square. So in a rhombus, the length of all of those are the same. In a parallelogram, those two are different. So if we had these, we can use vectors to determine if it is a parallelogram. All we need to find out is if AB and DC are parallel and AD and BC are parallel. But not just being parallel, they actually have to be the same vector. Otherwise it's going to be like weird shapes. Weird shapes. So let me write that down for us. This is the important thing. Those two vectors, if they are the same, then it's a parallelogram. That distance, that vector going from there to there, and that one is the same, and that one are the same, then it's a parallelogram. We can expand on this by talking about the lengths. If those two lengths are the same, then it's a rhombus. So let's get that down. What I've written is, if AB equals AD, then rhombus. Now what I mean by AB equals AD, I've not written the vector sign on there, and I've not written magnitude, you know, the straight lines up, because if I'm not writing the arrow in this situation, that means I'm talking about the magnitude. So the magnitude, length, of this one is equal to the magnitude of this one. Equally, we could have said that one and that one. But really, if you've already established that they're equal, we just need to establish that they're the same length as well. That's all we need to do. This is all the questions, like the geometrical questions that you're going to get in A-level maths, really. Is it a parallelogram or a rhombus? That's whenever a question says determine the nature of, or describe the quadrilateral, it's saying, is it a parallelogram or a rhombus? That's all it says. So let's do an example. These are our, what are they? I might do that again. No, we'll leave it. These are our position vectors to 4 locations, right? The question is, what is the question? It's describe the quadrilateral, as in saying, what is it? Is it a parallelogram or a rhombus is really what it's asking. Just right now, I'm going to say this board makes a lot of noise. I hope it isn't that annoying for any recording. Anyway, so what we first need to do is find out whether these vectors are equal. But one trick that I think here is that if you find these kind of questions tricky, draw a picky. Now, another teacher told me that. Someone else told me that. If you find it tricky, just draw a little picture. So we're going to draw a little picture. So let's say origin is there, then this is kind of like what we're dealing with. I've just drawn, like, I've said that's the origin there, and I've just drawn it, like, you know, to a bit of a rough scale. So what we need to find out is, does DC equal AB? So how can we find out what AB and DC is? Well, we're just going to go through each of those, and then that's it. So let's get started. Nice one. Can we see this? Is it on the screen? Only just. So what we've got is we've got the AB and DC are the same. Now I'm going to do it again because I need to work out if AD and CB are the same. I'm going to do the exact same process, but since I'm running out of space, I'm going to get rid of our little drawing. Yeah, I'll have to do that. What I've just found out is that they are the same, but I've got a minus sign in there. The minus sign is actually because I went B to C when really I should have gone C to B. If I still had my diagram, that would have been more clear, but without the diagram, I personally find it a bit difficult. But anyway, we know that, blah, 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 so we know it's a parallelogram. But we need to ask ourselves, is it a rhombus as well? So all we need to do is look at 2 of these vectors, two vectors which aren't equal. So obviously if we chose AB and DC, they're going to have the same magnitude because they're the same vector. So we're going to choose BC. No, let's choose AD and AB. So let's work out the magnitude of AD. It's just Pythagoras, remember? Got root 17. And now for AB. So that implies it's not a rhombus because they are not equal. I've got root 17 as one and root 5 as the other. Just off the corner there, I don't think you can see it, I've written not a rhombus. If you ever forget which one's a parallelogram and which one's a rhombus, just think rhombus has an S in it. That S means square. Parallelogram only has 1 R because parallel only has 1 R, but it's got 3 L's. That's it. This is everything for vectors. Now, vectors are a bit of an odd subject because in normal mathematics they seem a little bit like what's the use of them, but what we're moving on to is mechanics, and vectors are used in mechanics through and through. They are used for forces, for speeds, well, velocities, for accelerations, they are used everywhere because we don't live in a one-dimensional world. What we're going to do next though is I'm going to do one video where I'm going through some examples. So I'm going to have questions like this and I'm going to stick them on the board. We'll do them. And then after that we're going to move on to kinematics. I need a drink. Yeah, I'm happy with that. Sweet.